In this video, we introduce the concept of inverse functions, their properties, their notation, and when they exist. The next video will discuss how to find them when they exist. Let's start with an informal idea of inverse functions. Essentially, inverse functions undo each other. For example, suppose that f of x is 2x and g of x is x over 2. Then f undoes g because f composed with g of x is f of g of x, which is f of x over 2, and f doubles, so that's 2 times x over 2, which is x. Similarly, g undoes f, because g circle f of x is g of f of x, which is g of 2x, which is 2x over 2, which is x. We need the concept of an identity function to formally define inverse functions. The function defined by I of x equal x is called the identity function. We have the identity property for composition. That is, the function defined by I of x equals x has the property that for any f circle I is f, and I circle f is f. That is, when you compose any function with the identity, you get the function you started with. Let's relate this concept to other identities that you've seen before. The additive identity is 0. The additive identity property states that a plus 0 equals a, and 0 plus a equals a for all values of a. That is, the additive identity is what you add to a to produce a. Similarly, the multiplicative identity is 1. We have that a times 1 is a, and 1 times a is a for all values of a. So the multiplicative identity is what you multiply times a to give you a. In general, an identity is something you operate with that returns the value of the other input. Now let's define inverse functions. Two functions f and g are called inverse functions, provided f circle g is I, and g circle f is I, where I is the identity function. In other words, two functions f and g are called inverse functions, provided f circle g of x is x for all x in the domain of g, and g circle f of x is x for all x in the domain of f. Essentially, this says that inverse functions undo each other. Applying them in succession leaves the input unchanged. As you probably expected, we have special notation for inverse functions. We use a -1 exponent to denote inverse functions. When f and g are inverses, we write g equals f with a -1 exponent, read f inverse, and f equals g inverse. It's important not to confuse f inverse with 1 over f, since a -1 exponent on a real number means to reciprocate. F is not a real number, f is a function, and a -1 exponent on a function means inverse function. Let's connect this idea to other inverses that you've seen before. The additive inverse of the real number a is the number minus a. Recall that a plus minus a is 0, and minus a plus a is 0. So additive inverses add to the additive identity. The multiplicative inverse of the non-zero real number a is the number 1 over a. Recall that a times 1 over a is 1, and 1 over a times a is 1 for all a not 0. Multiplicative inverses multiply to the multiplicative identity. Similarly, we have inverse functions composing to the identity function for composition. Let's consider a couple of examples in which we verify that two given functions are inverses of each other. Suppose that f of x equals x cubed minus 1 and g of x equals the cube root of the quantity x plus 1. We are asked to verify that these are inverse functions. For a solution, we'll compute the double compositions and see that f and g undo each other. First, we compute f circle g of x. By definition of composition, we get f of g of x. Since g of x is the cube root of the quantity x plus 1, we have f of the cube root of the quantity x plus 1. And since f of x cubes and subtracts 1, we get our input cubed and subtract 1. Cubing a cube root removes the radical, and we get x plus 1 minus 1, which equals x. Since composition of functions is not in general commutative, we have to explicitly compute g circle f of x as well. By definition of composition, we get g of f of x. But since f is x cubed minus 1, we get g of x cubed minus 1. And since g of x is the cube root of the quantity x plus 1, we get the cube root of the quantity x cubed minus 1 plus 1. Because the radical sign is an implied symbol of grouping, we simplify the radicand to get the cube root of x cubed, which equals x as desired. Therefore, the functions f and g are inverse functions. A natural question to ask at this point is, does every function have an inverse function? There are a few issues to consider in answering this question. First, recall that functions cannot have repeated inputs. Notice that when we compute f of g of x, the outputs from g become the inputs for f. And when we compute g of f of x, the outputs from f become the inputs for g. Essentially, inverse functions will have reversed ordered pairs. Therefore, for the inverse to be a function, the original function cannot have repeated outputs. Functions with no repeated outputs are called one-to-one functions. A function, f, is called one-to-one, provided that equal outputs have equal inputs. In mathematical language, this means that f of a equaling f of b implies that a equals b. How can we tell whether a given function is one-to-one? Algebraically, we can check whether f of a equal f of b implies that a equals b. If it does, then the function is one-to-one. If not, then the function is not one-to-one. If you can find at least two x values that produce the same y value, then the function is not one-to-one because you have repeated outputs. Since horizontal lines represent y values, there's a horizontal line test for one-to-one functions. If every horizontal line intersects the graph at most once, then the function is one-to-one. If a function either increases or decreases on its entire domain, then it will pass the horizontal line test and will be one-to-one. Let's consider two examples. Is f of x equal x squared a one-to-one function? Let's compute the algebraic test. Suppose that f of a equal f of b. That is, suppose we have equal outputs. Then by definition of f, a squared equals b squared. We can take the principal square root of both sides of the equation, since the principal square root is a function. But we get that the absolute value of a equals the absolute value of b. Thus, a equals plus or minus b, and therefore f of x equal x squared is not one-to-one. Alternatively, you might think of a graphical reason why this function isn't one-to-one. Let's consider another example. Is g of x equal 3x plus 5 one-to-one? Again, let's conduct the algebraic test. Suppose that g of a equal g of b, that is, that we have the same or equal outputs. Then by definition of g, 3a plus 5 will equal 3b plus 5. Subtracting 5 from both sides yields that 3a equals 3b, and therefore a equals b. Hence, we can conclude that g of x equal 3x plus 5 is a one-to-one function. Alternately, you might think of a graphical explanation that g is a one-to-one function. Why would it matter if a function is one-to-one? We have a theorem that states a function f will have an inverse function if and only if f is one-to-one. Thus, only one-to-one functions will have inverse functions. In the next video, we will show how to find the inverse of a one-to-one function.